Why?
Change the direction.
Because where is it at in its oscillation?
The body.
Top or bottom?
The body.
Bottom. And then you're going to come up here, and you need to go back to T. Okay, so what is the slope of my velocity time graph?
Acceleration.
Acceleration. Okay, so then I can get my acceleration. So if this is my velocity time graph, what's going to happen with my acceleration time graph? Where's it going to start?
Bottom.
It's going to start. It's either going to start at a big positive value, 0, or a big negative value. Why bottom?
It's spinning up and you have a
And
negative.
the
Because
negative
of the only force that's
negative,
been used
negative.
is
Well, look at these slopes.
Negative.
Your velocity time graph has negative slopes. The slope of your velocity time graph gives you acceleration.
That's what it's saying.
So that's going to have some negative acceleration. Now, when is your acceleration time graph going to go through 0?
In the middle.
Why?
because that's whenever the velocity is max and the forces are equal to each other.
And also, when the slope of that tangent line on that acceleration time graph is 0. Oh, okay, so I'm going to start here at t over 4. That's when that's going to go to 0. So you're going to get some becoming action like this. So at that point, when your acceleration is equal to 0, sum of the forces is going to be 0. Okay? Doesn't mean there aren't forces acting on the spring.
No.
It just means that at that single point in the middle of that oscillation, that's when everything adds up to equal to 0. Cool. Let me see. A max, if we wanted to find that value, Km over, or Km times A. Okay?
Nice.
So in this situation, you'd have, and technically this is like a negative value. So you'd have negative 100 newtons per meter, mass of 1 kilogram, and then the amplitude is 0.1 meters, and you get 10 meters per second squared. Now, how this system is defined, is that going to be a negative or a positive value? Negative, because we're defining it as starting up here, and it's going to fall. Okay? Let's say I gave you this problem. At 1/4 amplitude, what percentage is U and what percentage is kinetic? So there's a couple of ways you can do this. One option is that you can just do like smash mouth physics. Okay? That's fine. So at any point, what does your U and your kinetic energy have to add up to?
Maximum.
And that maximum energy was 0.5 joules,
Yep.
right? So at some point, everything has to add up to 0.5 joules. Now, this is where you can do a little bit of trickery. Okay, just a little bit. So that 0.5 joules is going to be 1/2 whatever that kx squared plus 1/2 m v squared equals 0.5 joules. Right? Everybody cool with that? At any point, this works at any point. Everything has to add up to 0.5. So what you want to be able to do is look at the extremes. So what's the only time x is going to equal the amplitude? Maximum top or bottom, right? Well, if x equals your amplitude, you're at the top or the bottom.
AT's nothing.
What's your kinetic energy going to be? 0. Okay? So it works on the extremes. Okay? So at any point in between, this is what you have. So, could I do this? Could I say that that's 1/2 KA squared, right? Okay, which would be your maximum kinetic energy. Okay, cool with that. So, but we said that that's as that maximum in terms of x. We said at that point instead of a, that's going to be a over 4. So we could put that as 1/2 a. Or I want that to be, that amplitude is 1/4. Actually, I screwed that up. I'm going to make this 1/2. I was looking at the next step downward to get squared. So this is going to be 1/2 k times a over 2 squared, right? Okay. So this becomes, and if you, this is where if you wanted to, you could do smash mouth physics. You know the K value is 100 newtons per meter. You know the amplitude is 0.1 meter. And you can divide that by 2 and square it. Now, so plus 1/2 mv squared equals 0.5 joules. Okay, so that is still there. So when you do this, okay, a over 2 is obviously going to be 0.05. So if you wanted to do smash mouth physics, you could take 0.1 and divide it by 2, square root of that. Multiply that by 100, take half of that. And if you do that, what do you get? So somebody take your calculator, do the math. Take 0.1 divided by 2, otherwise known as 0.05, and then multiply that by 50. 0.125 joules. So if you wanted to find the percentage that was U at that point, what could you do? Yeah, take 0.125, divide it by the, and there's your percentage. Okay? Now, at this point, knowing this is 0.125, that's the value of your U. How could you figure out how fast it was going?
0.5 minus that gives you a K.
Yeah, because this plus my kinetic energy has to add up to 0.5, right? So if I do that, I subtract that out, I can figure out my kinetic energy. So you should be able to do this at any point along the way. A over 4, A over 8, whatever it is. Okay? And you should be able to say, okay, this is how I can figure out how much kinetic energy there is, how much potential energy there is. If I ask you to drop, no, I swear to God, Gavin, you ever touch anything in my room again, a magnet, a spring, anything, I'm just going to kick you out. Is that clear? Because you have ruined this, created a distraction for everybody. Because you think you can play around and not have to focus. So are we clear? Yes, sir. Touch one thing, you're gone. Okay? When do I teach you school? Shit. If I were to ask you to draw a graph of potential energy and kinetic energy versus time, what would the graph look like?
So the inverse of each other, like they all they have to add up to 0.5.
Okay? At any point, what do they have to add up to? 0.5. So if you're going to start at the top of the oscillation, what's it all going to start off at?
Potential.
Right? And you're not going to have any kinetic. So as time goes by, U is going to become smaller. So when's U going to reach 0?
Equilibrium.
The equilibrium point. What's your kinetic energy going to do?
It's going to go up, and it's going to be maximum.
Okay? Right? Now, as long as it's not a dampened motion, This is just going to look like a DNA strand.
Yeah.
Good. Now, keeping that in mind, let's say I gave you this problem. I will take a cart that has a spring, okay? And I'm going to compress that spring a little bit, and then I'm going to let go of it, and then I'm going to have it roll to a stop. So what would the potential energy and kinetic energy graph look like for that situation?
It starts all potential, and then as the spring is releasing.
The highest.
So, back up, Elliot.
Oh, no,
So
it's all
this
right.
point up here is going to be what?
Total
Okay, what's the only type of energy I'm going to have?
potential.
In the
Yeah.
spring, right? Okay, that's just going to be some amount of energy in the spring. I'm not going to have any kinetic energy. So I've compressed it some distance, and then that's going to roll, and then it's going to come to a stop. Let's actually make this in terms of distance. So my initial distance here, that's going to be 0. So if I'm going to compress it a certain distance, and then I'm going to have it roll away. So that's the equilibrium point. This is going to be important. This is going to be the equilibrium point. This is where it's been compressed. So it's all going to start as us. So when it reaches this equilibrium point, what's us going to become when it reaches that equilibrium point? 0. So my us is going to go to 0. What's my kinetic energy line going to do? It's going to go up, right? Because energy has to be conserved. What do you know about the top point on that kinetic energy line versus the us line? They have to be the same, because energy has to be conserved. Then, what's my kinetic energy line going to do?
Go back down.
Go back down. Why?
Stop.
Slowing down, right? Slow down, get to some distance here, right? What's my potential energy line going to do?
Just maybe horizontal.
Horizontal at 0? Why?
Because it's gone. There's no more potential.
It's gone. Okay, so that's just going to stay at 0. Okay? What would happen if I compress the spring further?
More, more than 18.
More total energy.
So the graph would just get bigger and longer, right? It would roll further before it stopped. What would the graph look like if that was a perfectly frictionless cart? The only thing that would change is your kinetic energy would stay the same. Okay? Assuming that there is friction when I let go of this. Let's go old school. Old school.
V equals V naught position.
No, not that old school.
That was in there.
Is work being done on the cart as it rolls?
Force on the distance.
Right? Work equals two general broad ideas. It equals force times distance, and it also equals, in a broader idea, a change in, or just change in energy. Okay, it doesn't have to be kinetic, it could be potential. Okay, change in energy. Right? Now, what type of energy am I initially storing? Which would be calculated by doing what? 1/2 kx squared, right? Let's play the what if game. So, if this is the graph, if I compress it 1 centimeter and let it go. So that was just compressing it 1 centimeter. What would the graph look like if I compressed it 3 centimeters?
More work, 4 times.
Why more work?
More 4. More energy.
Talk the energy side of it. If I triple the distance,
By 9.
9x.
oh, that goes up by a factor of 9. Oh, that's a big jump in the energy, right? That goes up by a factor of 9. what's creating the force? This is old school. What's creating, no. This is after it's rolling. Okay? After it's rolling, what's creating the force to make it stop? Friction. If I triple the compression, what's that going to do to the frictional force making it stop?
One distance changes.
Hold on. Don't talk about
The
this.
frictional force doesn't change.
Why not? How do you calculate force friction? Force friction equals what? U times old school. Force friction equals U times force normal. Old school. Old school. So what's the only thing that determines the force friction? U and is how far I compressing the spring have any bearing at all on that? Not at all. No bearing whatsoever. So if I triple the distance, what's going to happen to my energy? It's going to be 9 times greater, right? So if this goes up by a factor of 9, and my force stays the same, distance has to increase by a factor of 9, assuming that the friction force stays the same. Okay? So look for that on our test question here. Okay? I'm just saying. There might be something to think about.
Do we have a review sheet?
Yeah. Let's see. I think that's one. I know it may sound people have to get out of here. So if I were you all preparing for this test, okay, make sure that you do like that problem where it's like a period or a pendulum of an oscillating mass or a simple pendulum on Earth, and then we compare that to what happens like on Jupiter. If you want like some practice, what you could do is you could go to that PhET simulation with springs, because that's cool because you can set up different parameters. Hey, you can make predictions. You can say, okay, hey, I'm going to set a K value of whatever. I can put a known mass on there. I can try and figure out what that oscillation is going to be. So that's something that you might consider if you want like some practical application. Okay? You might consider a problem like this and play the what if game. Like, okay, I worked it where I compressed it 3 times greater. What would happen if we did it 4 times greater? What would happen if we compressed it half as much? Okay? What would the graphs look like? Okay? What would be that relationship between how much you compress it and stopping distance? Okay? Can you find a way to express that relationship mathematically? Okay? So, but I'm just telling you tomorrow, just remember, work equals 2 things. Force times distance and change in energy. And if something's stopping, what's the force? Okay, Southeast, you're out. Please stop the camera tomorrow.